Welcome, students. Recall, in last class, we were trying to make sense of the homogeneous differential equation a y double prime plus by prime plus cy equals to 0, where a, b, and c are constants. Out of that, we got the characteristic equation ar square plus br plus c equals to 0, and we have dealt two cases already. So there are three cases. Case one was two distinct roots, that is already dealt. Two complex conjugate roots, that is already dealt. And so we are dealing with now case three, the repeated roots. So how do you get the repeated roots? So you have ar square plus br plus c equals to 0, and you have with b square minus 4ac equals to 0, right? Recall, if you have a quadratic equation with b square minus 4ac equals to 0, then the roots of those quadratic equations are repeated. By quadratic equation, I mean ar square plus br plus c, all right, of this form. So now we want to handle this case. So note that in this case, we'll have R1 and R2 both to be minus b by 2a, because the solution is given by plus or minus b square minus 4ac over 2a, and this part is equal to, and this part is equal to 0, right? So now we want to deal with the case. So, well, one solution is e to the power minus b by 2a. Now I cannot take, so this is a solution, right? However, we need, for fundamental set, we need two solutions, right? Like say, for example, if you have the characteristic equation, let me call this as short as CE, the characteristic equation is given by r square minus 2r plus 1 equals to 0. In that case, we will get the solution of this is r square minus r minus 1 square is 0, and then the solution y1 is going to be e to the power. So here you get r1 equals to 1 or r equals to 1. That's the only solution. So you get e to the power t. The question is, what is the second solution? Because we need two solutions which are linearly independent to make the fundamental set, right? So we need two solutions. So how do you hunt for the second solution? So let's derive the second solution. So we'll postulate, we'll guess, we will postulate. Postulate is a guess that the second solution takes a form from y of t equals to same as y1 multiplied by some function v of t, yeah, where v of t is some function that needs to be determined. Okay, so we are postulating this as a solution. Yeah. Now one may ask the question, why would my solution will be of this form? Why not something else? So let's work on this and see if there is such a VT which satisfies uh, that it's a second solution and makes the fundamental set. Okay. So we have, so VT is going to be e to the power y1 is minus b by 2a t, right? So now let's try to see condition on on Vt by substituting this into the equation ay double prime plus by prime plus c equals to 0. So substitute y of t in this to find more information about to find v of y. So let's just do that. So we have y prime is going to be d by dt of vy1 prime, which is going to be v1 y1 plus v prime y1 plus v y1 prime product rule. Similarly, if you look at y double prime, then that is going to be derivative of d by dt of v1 y1 plus vy1 prime, and that is going to be v double prime y1 plus 2 v prime y1 prime plus v y1 double prime. I'm using here an Euler formula, so it's a good exercise. Euler's formula for if I have to take u v and I want to take nth derivative of this, then this is going to be summation I equals to 0 to n u n choose I u I, that means ith derivative of u times v n minus I derivative of v. So this is Euler's formula. You can prove it using mathematical induction, or and in this one, in our work, we can assume this result, but you can prove it easily using induction. Okay, so this basically gives you an easy way to find out the nth derivative of a product. Otherwise, you could basically go and use product rule twice here and get to the same answer, right? Okay. So now our differential equation is, so D is ay double prime plus by prime plus cy equals to 0. And let's substitute now our y double prime, which we got here, y prime, which we got from here, into this equation. So we get a times v double prime. I'm going to write this whole thing here, y1 plus 2 v prime y1 prime, this has to be y1 prime, plus v y1 double prime, plus b times, what is y prime? We have already computed that. So v1 v prime y1 plus v y1 prime plus c v cy, which is simply v times y equals to 0. So here we were supposed to find v of t. Okay. So now we need to simplify this a bit. So I'm going to collect all the y double primes, y primes, and so on and so forth. So let's see. So I'm going to collect the following. A, I'm collecting this, this, and this. So if I take A common, and I can take also V common from it, so I get A times V, I get, oh sorry, we can only take V common. So we have A y1 double prime plus B y1 prime plus C now plus B y1. So I'm going to collect the other ones now. So I'm going to collect everything else on the separately. So what do I get? I get this term, this term. All right, so let's see what is that, and then we get this term. So let's collect that together. So we have a v double prime y1 plus 2 a v prime y1 prime plus b v prime y1 equals to 0. So this part is going to be 0. Why is that? Because this is satisfies DE, right? Since satisfies DE, right? Because your DE is that a y double prime plus by prime plus c equals to 0. And in this equation, we already have started with the fact that y1 is a solution, right? So we have already started with y1 equals to solution. So let me just say that to start with. So y1 is one of the solution. So then we get, so this is 0. So we are left with this guy here. And let's put back now what your y1 is. So your y1 is e to the power minus 2 by a, sorry, minus b by 2a t, right? So your y1 prime is going to be minus b by 2a times e to the power minus b by 2a t, right? So now let's substitute this in the remaining part of the equation here. So what do we get then? We get, so first one is y1, so a times v double prime, which we don't know yet, which we are trying to find, times e to the power minus b by 2a t plus 2a v prime y1 prime, which is going to be minus b by 2a times e to the power b by 2a t, and then b times v prime y1, which is going to be, what is your y1? y1 is e to the power minus b by 2a times t. This equals to 0. And simplification of this will give some condition on v double primes, and that will help us solve the problem. So now this implies a v double prime e to the power minus b by 2a t. Now notice that this 2 and this 2 will cancel. There's a minus b here, and then there's a plus b, so they will cancel out each other as well. Let me just write that down. These guys cancel out, so these guys cancel out. What am I left with is plus, or rather minus b v prime e to the power minus b by 2at plus bv prime e to the power minus b by 2at. And these guys will make 0. So therefore, this gives us a v double prime e to the power minus b by 2a t equals to 0. Now a is not 0. Otherwise, this is not a second order differential equation. Also, e to the power minus b by 2a t is not 0. Why? It's an exponential. E to the power x is never 0. So this would imply v double prime t equals to 0. This would imply v prime t is some constant this will imply v of t is constant times t plus some other constant, say k. Now we can choose. So what is the solution? We can choose. So since we need another solution, so choose c equals to 0, sorry, c equals to 1 and k equals to 0. So what is your solution then of form? Because you will have yt equals to v of t times y1. This is going to be, let's just take ct plus k times e to the power minus b by 2a t. Now, again, I chose c1 equals to 1 and k equals to 0. In that case, I will get t e to the power minus b by 2a t, because I need just one solution, right? Now I get this to be my, let's call this as y2. So this is going to be y2. So this is what is your y2t. Now you may say, why didn't you choose c equals to 0 and k equals to 1? In that case, you'll get back to y1, all right? So the idea is to get another solution y2, which is linearly independent with y1. And what does that linear independence means? It means that the Wronskian of y2 and y1 must be non-zero. Okay, so now let's check if the solution is fundamental. So how do you check that? Again, you'll use the Wronskian to check. So what are the two solutions we got? So the solutions we got was y1, y2 is e to the power minus b by 2a t, and the next solution was t times minus b by 2a t, and so we'll use Wronskian to check. Use Wronskian to check if the solution is fundamental. If this set of solutions is fundamental. That's what it means by solutions being fundamental, is that this set of solutions being fundamental, all right? So this set of solutions is fundamental. So let's compute the Wronskian. So y1, which is y1 prime y2 prime. Now I have to use product rule here. So first derivative of t is 1 times e to the x as it is, plus t times derivative of this exponential, which is going to be minus b by 2a in the bracket times e to the power minus a by 2b, sorry, b by 2a t. So let's compute determinant of this. Now, if you check the algebra, you will see that e to the power minus, this is going to be e to the power minus b by 2a t, which is non-zero. Yeah, so check the algebra. Yeah. Check algebra. So therefore this means, since it's non-zero, this means y1 and y2 form a fundamental set. Now note that this is a second order differential equation. So the fundamental set will have two functions in it. If there is a third order differential equation, the fundamental set will have three. Okay, so we'll have a generalization of Wronskian in an appropriate manner. We'll see that later. So let's summarize what we have discussed in this last section. So a general solution of a constant coefficient homogeneous differential equation, a prime plus by prime plus cy equals to 0 is determined by the roots of the characteristic equation. Right. And if there are three cases about the roots, either the roots are real and distinct, say called R1 and R2, then the solutions are, general solution is given by y of t to C1 e to the power RT plus C2 e to the power RT. Sorry, R1t and R2t, right? These are the superimposition of these two solutions. Now, suppose we have a double root, then we have yt equals to C1 e to the power R1t plus C2. Now you just multiply that with another t, so you get CR1t, right? So we have this as a solution. Let me just call this as R because R1 and R2 are same. So RT times T times e to the RT. So you see this is an extra multiplication by T. Okay. Now in case of complex conjugate, we have again the same way, but we made the solutions real. So the solutions are yt is C1 e to the power lambda t times cos of mu t plus C2 e to the power lambda t sine of mu t. Okay, so mu t is not a function. Mu multiplied by t. Mu is a, well, you see r equals to lambda plus or minus I mu t is the solution to the characteristic equation. So mu multiplied by t. So this is the setup. All right. So this takes care of general solution of second order homogeneous differential equation with constant coefficients. Now, what about non-constant coefficients? Okay, so let's work on that. So a similar approach can be used to find a second solution in case of double root, can be used to solve more general problems. Now consider the homogeneous differential equation y double prime plus p of ty prime plus q of ty equals to 0. And we already know one solution, which is given to you as y1t. Now note that there's no corresponding characteristic equation here. Our characteristic equations are, at least for now, are restricted to a homogeneous differential equation with constant coefficients. So these coefficients are not constants, right? You can see that this is a function of t, and this is also a function of t, right? So these are not constant coefficients. So this is a different, it's still linear though. So it is, what is the difference? So linear, still second order, and homogeneous as well, because this is 0, right? So homogeneous as well. Okay. So there's no corresponding characteristic equation here, but suppose on top of this we are given one solution y1t, and we want to find out the second solution. All right, again, what kind of second solution? Not any second solution, but a solution which will, say, y2, which will along with y1 form the fundamental set. All right, so that is the goal. So we'll do the same thing as we did in the earlier one. We'll assume the solution is of form, postulate the solution is of form vt y1 as your y2t. So let's do this now, and we are hoping to find out v of t. So for some v of t, which will be determined. So substitute. So substitute y2 equals to vy1 into the differential equation above. Which differential equation I'm talking about? This differential equation here into this differential equation. Okay, so when you substitute, what do you get? You get, we have again y2 prime equals to derivative of this, so there's going to be product rule v1 y1, sorry, v prime y1 plus v y1 prime, and y2 double prime, again using the Euler's formula, will be, it's like basically expansion binomial theorem for power 2, but instead of power there are derivatives. So second derivative of that, y1 plus 2 v1 y1 prime plus v y1 double prime. So what do we get? So we get our differential equation. So 0 is equal to, I'm going to substitute these guys into the differential equation here. So what do I get? I get v double prime y1 plus 2v prime y1 prime plus v y1 double prime. That's just the first part here. Now second part, plus p of t times v prime y1 v prime y1 plus v y1 prime plus q of t v y equals to 0. Well, it's already here. Now out of that, again, I will bring few terms together. So namely, I'll bring this guy and this guy and this guy together and take v common. So v times y1 double prime plus p of t times y1 prime plus q of t times y1, and then whatever remains we keep it on the side, so we get 2 y1 prime plus p y1, right, times v prime plus what, plus y1 v double prime equals to 0. Okay, now this is going to be, this part is equal to 0, right? Why? Because it satisfies, since it satisfies the d, right? Because we are starting with the solution, y1 is the solution, right? So y1 will satisfy this equation. So now what are we left with then? We are left with, so v y1 v double prime plus 2 y1 prime plus p of y1 multiplied by v prime equals to 0. So now this is a second order the in v, right? So again, solving for v would correspond to solving a second order differential equation. I mean, you didn't really get much out of it. Yeah. However, that's not quite right, since there's no constant here. So since there is no constant term. There is no term in V. What we can do is the following. We can do reduction of order. So the idea behind reduction is take Z equals to V prime. This would imply Z prime equals to what? V double prime. And therefore, star reduces to y1 z prime plus 2 y1 prime p y1 times z equals to 0. Now we have reduced the order. So we have reduced the order of the from 2 to so this and this can be solved. This can be solved using techniques of first order differential equation, right? Of linear first order differential equation. What are the tools we have? We have basically there we have tools of either separable differential equation or first order differential equation using integrating factors. So to find zt, so you first find zt and then integrate zt to find what v. So let's see an example along this line. So given here, so given that y1 t equals to t square is a solution to the differential equation, find a second solution y2 such that y1 and y2 become the fundamental set of the solution. Actually, it should be a fundamental set because there are many fundamental sets, right? If you have y1, y2, then any constant, non-zero constant times y1, comma any non-zero constant times y2 is also a fundamental set of solutions. So I should use the word not the. Okay. So before I go and proceed to find y2, I should first check if y1 is a solution. So check if y1 equals to t square is a solution given the, right? So how do I check? So let's see. So what do I get? I get y1 prime is 2t and y1 double prime equals to 2. So left hand side of the differential equation is t squared times 2 minus 4t times y prime, which is 2t, plus 6 times t squared, because y is t squared. So we get what? We get 2t squared minus 8t squared. So 2t squared minus 8t squared plus 6t squared. And that is indeed 0. So therefore, y1 is a solution. So therefore, y1 is a solution to above differential equation. Now let's proceed to look at the to find the second solution. So you have, so you can either basically work right away with this here because this is what you have found out, or rather you could directly work out with this one here, or let's just go through the steps of reduction again. Okay. So now postulate y2 equals to v y1. So this implies y1 prime. This implies this is same as y2 equals to v times t square. This implies y2 prime is 2tv plus t square v prime, and then we get y2 double prime equals to, again I prefer using the Euler's formula, so I get v times second derivative of t square is going to be 2, then 2 v prime t square prime, which is 2t, and then what else do I get? Plus t square times second derivative of, so I substitute this now, substitute in differential equation, substitute in above differential equation. So we get what? We get t square times y2 double prime plus, sorry, minus 4 t y2 prime plus 6 y2. Now this is a solution, then this must turn out to be 0, right? So this must be 0. So let's see, what do we get? So we get t square times v double prime t square. So I'm going to write the same thing again. So v double prime t square plus 4 v prime t plus 2v minus 4 v prime t square plus 2tv plus 6v t square. Now let's expand this out. So we get v double prime t to the power of 4 plus 4v prime t cube plus 2v t square minus 4v prime t square plus 2tv, sorry, my bad, no, minus 8tv, right? Multiplies out. Minus 8tv plus 6v t square. Now let's see what other things we can cancel from here. So we have 4v prime t there is, this equation was 4t, so there has to be a t here. So in that case, the power gets bumped to t and then t square. Okay, so now let's work it out. So plus 4tv square, this cancels out with this. Now the remaining part, 2vt square plus 6tv square becomes 8tv square, and that cancels out with this guy. So what is really left out is v double prime t to the power 4 equals to 0. Right? Now, therefore, what should happen? So this is always 0. So therefore, v double prime must be 0. This means v of t is sum c1 plus c2 times t. Again, you can pick c1 equals to 0 and c2 equals to t. Sorry, c2 equals to 1. So therefore, v becomes what? V is t, and y2 equals to v y1, which is t times t. What was it was t square, so v times t times t square, which is t cube. Yeah, so we are guaranteed that this is a second solution. So we got, therefore, y1 and y2 are y1, y2 equals to t square t cube. Now check if form a fundamental set. Now, how are we going to do that? We'll compute the Wronskian. So Wronskian of y1, y2 at t is going to be determinant of y1, which is t, derivative of that, which is 2t, then y2, t cubed, derivative of that is this guy, and when you simplify, you get 3t to the power 4 minus 2t to the power 4, which is t to the power 4, and that is not identically 0, right? It's not 0. So this is not 0 if t is not 0. Therefore, y1, y2 is a fundamental set of solutions. So that's about it. Thank you very much for your attention.